combinational logics. So what are the combinational circuits? First we know about the maybe some of you already heard about adders, subtractors, comparators, encoder, decoder, multiplexer and demultiplexer. These are all the components we can say that they are the combinational circuits or used in the combinational logics. Before going to the combinational logics, let me give you a brief background that about digital circuit and the branches of digital circuits, so that it will be helpful for you to understand combinational logics or combinational circuits. First of all, digital circuits are of two types, because we are studying digital, we are not studying analog communication, and analog circuits are totally different, which we already discussed in our early lectures. But in digital circuits, we can say that circuits can be of two types: combinational circuits and sequential circuits. So we will be studying about combinational circuits, but to see the difference between them, here are some of the points which I will deliver for you. The first point is, in combinational circuits, output depends only on present input. This means in the combinational circuit, only what matters is your input, because your output will be depending on whatever input you are giving to your system. But in sequential circuits, output depends only on present input as well as previous output. In combinational circuit, only input is important, but in sequential circuits, input as well as previous output, the output of your previous you can say system or previous procedure, is also important in sequential circuit. Second point, adders, subtractors, multiplexers, demultiplexers and read-only memory. These are the examples of combinational circuits. What are the examples of sequential circuit? These are flip-flops, counters and registers. Examples: how is the adder example of combinational circuit? We can see in the adder, if we plus 1 plus 0 is equal to 1, so the answer 1 depends upon the two inputs we are giving to it, like 1 and 0. So as from the definition it's clear, output depends only on the present input. So in the adder we give two inputs and the output depends upon the inputs. For example, if we give 1 plus 0, it will be 1. If we will give 1 plus 1, it will be 2. So it all depends upon the input of the combinational circuit. What about the sequential circuit example? Counter is the example of sequential circuit. For example, how the counter works: 4 plus 1 is equal to 5, so input. Now the second time, 5 plus 1, 5 is the output of the previous procedure, and it will add one input, so the output will be the combination of input plus the output of the previous procedure. Same, 6 is output, so 6 plus new input 1, the answer is 7. So in the counter, we'll always add something into the answer of the previous procedure. What are their logical shape or design? This is the combinational circuits. Here we have inputs and only outputs. Outputs will because depends upon the inputs. But in the combinational circuit, there are inputs, outputs, but as memory unit. Why we are using memory unit? Because it will use the answer or output of the previous procedure, so it will be stored in the memory. Because in counter, like 4 plus 1, 5 was the answer, so 5 was saved in the memories unit, and in the next procedure, it will add the output of the previous procedure from this memory unit. So the only difference you can see is the memory unit, and this memory unit helps sequential circuit to add the output of the previous procedure. So what are the combination logic? Let's start. A combinational circuit consists of logic gates whose output at any time are determined directly from the present combination of inputs without regards of previous output. It is the same thing which we were discussing, that a combinational circuit, it depends on the it consists of some logical gates, it can be any gates, and the output of those gates always depend upon the input we are giving to it. It does not require the output of any further previous procedures, so it's standalone. Just give the input and we'll get the output as per the inputs. Graphical display. The logical gate accepts signals from the inputs and generates output, so there is no memory unit, there is only the input, IPs and outputs. There is no memory unit because we don't use the output of the previous procedure or system. What are the applications? A combination circuit performs a specific information processing operation fully specified logically by a set of Boolean functions. It consists of input variables, logic gates and output variables. Used in ALU, arithmetic and logic units. So combination circuits are mostly used in ALU, arithmetic and logic units. It's also used in data transmission, and it also used in code converters. So these are the application in arithmetic and logic unit. In ALU, adders are the example, subtractors and comparators. These are the units which use combinational logic in ALU. In data transmission, mux and demux. Mux means multiplexer and demux means demultiplexer, encoder and decoder. You know, whenever there is a data transmission, why we use multiplexer? Multiplexer is something which you can say multiply, and demux multiplexer means demultiply, demux. In communication, a number of communication wires, lines or channels are coming, and before we send it to the main transmission line, we use this, and on the receiving side we also use mux and demux. So encoder and decoder are also on the receiving end on the transmitter sides for the encryption and decryption of our data. The third thing is code converter. In code converter, combination logics are used in binary, in BCD codes and in gray. So we can see that combination logics are used in all the types of equipments. Rather, it's a arithmetic and logic units, it's a communication unit, transmission units, or it's a coding converters. So now combinational gates. How gates are combined? I think we already studied this in when we did the Boolean algebra, Boolean expressions. So we will also revise it now. So here we are using gates in the combinational. First of all, before moving to this, I think I want to tell you that in next lecture we will study about the design rules for the combinational logic. So in order to understand more clearly about the design rules, we need to understand some of our previous topics like combination gates, truth tables and K maps, and these things we will also now discuss in today's lecture, so that in our next lecture it will be easy for everyone to understand the design rules. So now let's start our gates. gates in the combination. As you can see, there is a OR gate. OR gate is there, and there are some combinations of OR gate. What is the OR gate main function? I think we studied in our Boolean algebra. Whenever we use OR gate, this means we are adding the variables. So here, how many OR gates we are using? 1, 2 and 3. So let's start from the first A, B input. A and B is given input to the OR gate, and the output will be A plus B. C and D is given the input, and the output will be C plus D. Now we want to get the final answer of A plus B plus C plus D. So we will use one more OR gate. The reason of telling this to you is we need to revise the combination of different logic gates, and if we want to add some variables, then we will use OR gate. This is the combination logic gate example of AND gate. So when we will use our AND gate is used whenever we want to have the product of variables. For example, A and B was the input and the output was A into B. C and D was the input and C into D was the output. So the final output with the AND gate was A dot B into C dot D. So whenever we want to use whenever we want to take the product of the variables, we will use AND gate. Now it's the same, like we no need to confuse about AND gate and the NOT. You can see here a NOT. So what is a NOT? What is the purpose of the NOT? We already studied about this. It will give the opposite, or it will give the here also we are using NOT gate. So the simple output of AND gate will be A into B, but here it is NOT gate, so it will be A into B bar and A into C into D bar. So the final will be also changed because of the NOT gate. It's also the same example of OR gate, just we add the NOT gate and it will be bar here and the inverse of the answer also. The final example is, here we are giving different types of, here we are using OR gate, here we are using AND gate, and here we are using NOT gate too. And with the combination of all these gates, we are getting the output. So in combinational gates, we can use different gates for getting our required output. So next, our fifth lecture is design steps for a combinational circuit. But before that lecture, I want to revise few things which will be helpful for us for the next lecture. The first thing is we need to use to draw K-map from our truth table. I think we already did this, but I want to revise this here. For example, we have a truth table here and we have to draw our K-map from this truth table. So how we will draw this K-map? Here we can see that we have 3 inputs and 1 output. So first of all, we need to make the 3 variable K-map A, B and C. So here all the variables are 0, so we will put the 1 here. A and B 0, 0, 0, 1, so it will be 0, 0, 1. 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So this is how we draw truth table K-map from truth table. So this will be using in our next lecture. Another thing which we'll use in our next lecture will be K-map to the logic diagram. How we'll make logic diagram from K-map. For example, this is our K-map. It is a 2-variable K-map and there are 4 cells in it, and we first of all what we have to do is to design our logic diagram. First of all we have to write the equation. So the equation for this is, remember in yesterday lecture when we were talking about the design, we all design rules for the K-map we studied as per equations are taken one as in SOP form. So this we will also take in SOP form. So in SOP form we always take the ones, we always ignore 0, but if we are taking POS form then we take 0. So here generally we take SOP form. So how many ones are there? Only 1. So what is the equation for this is, here it is 1a and it is 1b. So it will be AB will be the final equation for this K-map. So how we will draw our output from this? From here we can see we have 2 inputs. So first of all we will give 2 inputs, A and B. And what is the, it is the product. So whenever we want to find the product we put the AND gate. So we put one AND gate and our final answer will be A into B. So this is how we make K-maps, logical diagrams from K-maps. So this is the this is today's lecture in which we know about the combination logics. What are the combination logics? What are combinational circuits? What is the difference between combination and sequential circuits? And what are the applications of combination circuits? And in next lecture we will read about the design rules of combination logics, and in those we will using this K-map to logical diagram and also from truth table to K-map. So we already revised this. So thank you for listening for today's lecture.